Hello, this video is going to be on spans of vectors. I'm going to discuss with you what is a basis, how to create linear combinations, what it means to be collinear or coplanar. We're going to talk about linearly independent as well as linearly dependent sets and spanning sets. So let's start off by looking at this question. You're told to record u, which is given with magnitude in its direction relative to northwest. We want to write it as an algebraic vector. Part 1, using standard unit basis vectors, so that's the I hat and j hat. You've seen this before, and then we'll extend it with these two questions to this particular lesson so you could see the relevance of spans using this example. So let's first of all draw vector u. We have 45 degrees between the vector and the north line. And let's draw the vector u by itself so that we can create an x and y axis instead, because the I hat and the j hat are in the positive x direction and positive y direction respectively. And these are unit vectors, and that's what the little hat means, that they're size 1. Then, to be able to convert this vector into component form, we need the angle from positive x-axis. So that happens to be 135 because we have 90 degrees plus the 45-degree angle. So question number 1, this vector u will now be converted using magnitude cosine of this angle and magnitude sine of the angle for the two components x and y. And that ends up being perfectly negative 5, 5. Which means that you take vector I hat, you reverse its direction in the opposite direction, and you're going to have 5 of them, and then up 5 of j hats, and you will arrive at the end of this vector itself. So this is not anything new. Now we're going to go on to question 2. So question 2, what we want to do is take vector u and use vectors v and w as the basis instead of this I hat j hat. So here is the two vectors drawn. We have v left 1, 3 down, and w is 2 to the right, 1 up. So what I'm going to do now is remove the Cartesian coordinates there, so we can just see just the vectors themselves. And I'm going to take vector u, this blue one, and draw it at the tails of the other two vectors. Then, because vectors v and w are supposed to be my bases, I'm going to extend a dotted line in the direction of this vector v, and same thing, a dotted line in direction of vector w. Then, you're going to take the parallel line to vector v and put it also not just at the tail of this blue vector but also at the tip. Same thing with this dotted line. Instead of having it just at the tail of vector, the blue vector u, we want it also at the tip. So it actually creates this parallelogram piece. Then what you will notice, just like we've been saying that there's negative 5 I hats plus 5 j hats, we want to see how many of these u's do we need and how many of these w's do we need to arrive at from the tail to the tip of this blue vector u. So I begin by eyeballing this, and then we'll do it algebraically. So we know we have to go in the opposite direction of vector v, and it looks like it's approximately 3 vectors to arrive at this parallelogram edge. And then in w also we want to go in the opposite direction, and maybe it's close to 4 of these w's, maybe it's slightly less. I was just estimating. I don't know if these values are correct or not. We're going to actually do this algebraically now to actually find what is this stretch factor on w to get the vector u. So what we're going to do, we're going to say that u is equal to some scalar multiple of v, so we don't know how much to scale this v, so my guess here was negative 3, but maybe I'm wrong, plus some sort of scale factor of w. So this b, I was guessing at it and saying it was like negative 3.8. We're going to now do it algebraically. So vector u We found it over here, negative 5, 5, using the usual Cartesian coordinates. And then leave the a alone and put the component form of vector v that's given and w. Then what you want to do is split up the components. So what's in front of the comma, negative 5, is equal to what's in front of this comma. We have negative 1a, so negative a, plus in front of this comma we have 2 with a b, so plus 2b. And then we want to create another equation with what's after the comma, so the y components. So 5 is equal to negative 3 with an a, plus 1 with a b, or just plus b. So we have two equations, two unknowns. So I'm going to take this second equation and I'm going to multiply it by 2 and place it underneath the first one, because that creates 2b and 2b, which we can eliminate by subtraction. So negative 5 minus 10 is negative 15. Negative a, subtract negative 6, there's a double negative there, so you get 5a. 2b minus 2b disappears. So a actually does end up being exactly negative 3, like I was guessing up here. So now we need to plug in a equals negative 3 into one of the equations, and we will get that b is negative 4. So I was slightly off up here, but that's okay. And so final answer for u in terms of v and w is negative 3 v's minus 4 w's. Let's proceed to do part 3 now. We have new vector v and w, and we want to see if they can serve as a basis here, just like previous question 2 did. So we, first of all, let's do it algebraically before we look at the picture. So we set up the same linear combination. This is called the linear combination, where you just stretch one vector and add a stretch of another vector to see if you can arrive at the third one. And so the original vector we had negative 5, 5, and then v is 2, 6, and w is 1, 3. So let's see what we get in this situation. So split up the components. This is the x component equation. This is the y component equation. Let's multiply this equation by 3 and record it underneath so we can subtract and eliminate b's. 5 minus negative 15 gives you 20. And actually here, not just b get eliminated, but also the a. So you get this contradictory statement. 20 is not equal to a 0. And so this means that v and w, they do not form a basis. Let's look at how this looks as a picture. So this is to remind you our vector v and w from question 2. We had the x and y axis here and we drew them. So I'm going to do the same thing with question 3. Let's first of all draw w, so that means we're going 1 over 3 up, and then v is 2 over 6 up. What do you notice? Both of these vectors fall in one line. So we call this collinear. So v and w in 3 are collinear, or another word for that is parallel. And any linear combination will only yield another parallel vector. You would not get something that is negative 5, 5, which is in this direction, the blue vector that we had there. It's impossible to do so. So this is a summary of what it means to be collinear, but we'll also extend it to be in 3 dimensions. We could also talk about something called coplanar. So let's start with this picture over here. We have vector u, and I have 2 versions for x, x1 and x2, 2 vectors. So this statement right here says that there is no way that you can stretch vector u by a factor of k and get vector x1. Well, look at it. U is pointing in this direction. No matter how much you stretch it, the direction will not change. It will never point in this direction. So we say that x1 vector and u vector are non-collinear. On the other hand, x2 vector, you can definitely stretch this vector u to have exactly the same size, magnitude as x2, because the directions match, or it could have been in the opposite direction. As long as they fall on the same line, we can say that they are collinear. That's why we use the word collinear, because they actually fall on the same line, and they could be facing in the same direction or opposite direction. So this right here is technically a linear combination, except we don't actually have any addition. It's just a stretch of one vector. So let's look at linear combinations with 3 vectors. So again, we have 2 versions, x1 and then x2. We're going to see which of the 2 vectors could be written in terms of the uv that are on this plane. So this parallelogram here is to signify that these vectors v, u, and x2 are on the same plane as each other, but this vector right here that pokes out of this parallelogram is to indicate that it actually is not on the same plane. So if you cannot find this statement to be true, that there is a stretch factor on k on u and stretch factor m on v, and you will get contradictions when you're trying to make it equal to another vector x, then this x1 and the other 2 vectors are non-coplanar, meaning one of the vectors is sticking out from the other 2 that create a plane. If you do not get contradictions, that means all 3 of them are on the same plane. We call them coplanar. So let's first of all do an example that concentrates only on the words collinear and coplanar, and after that we'll talk about these linear combinations and how to do this with algebra. So here we have a picture of a box with vertices labeled. Let's start off with part A. Name a point that is collinear with points E, H. So EH, I highlighted E to H in yellow, and we can see J is on the same line, collinear, as those 2 points. So point J is the answer here. Next one, collinear with BI. So BI, I highlighted. What else is on the same line? Well, point C is on the same line. Name a point that is not collinear with EH. So EH is this yellow. So any point that's not on this line, EJH, is something that we could quote, which I did. Name a point that is not collinear with BI, so anything that's not on the line BIC. So all of these are possibilities here. Part E, name a point that is coplanar with points DAB. So take a moment to draw a triangle from DAB and shade it in, as shown here. And I'd like you to imagine a plane that goes infinitely outwards from this triangle. So we can tell that point I and C actually will be on the same plane as this top part of this box. F, name a point that is coplanar with CGF. So CGF, again, draw a triangle, shade it in. So this indicates the back face of this box. So B and I are also going to be on the same plane as C, G, and F. For the next question, I erase everything I had before so it's easier to tell. We're going to name the intersection of the plane AEH and plane FBE. So first of all, AEH, shade in this triangle right here. And BFE, shade that triangle here. And where do they intersect? So remember that planes go infinitely in all directions from this triangle. So I'm going to extend this blue triangle. And I'm not going to draw it infinitely, I'll just stop at the face. And you can see that this blue shaded region and this green triangle overlap in this line, which is line AE. Now let's go on to talking about these linear combinations. Before we do that, I have a definition here. What is a spanning set or a basis set for a space? It is the smallest set of vectors from which you can create all the other vectors in a space. Now is a good time to discuss the types of spaces one can have. First of all, there's a one-dimensional space, which is just technically a line. It could be the x-axis itself, but it doesn't have to be in that direction. It could be in any direction at all. So here, that could be a picture for a one-dimensional space, which is just a line. We can have two-dimensional space, which we call the plane. this plane, usually we were defining it using the I hat and j hat to create the coordinate system in the x direction and y direction at 90 degrees to each other. But we do not have to have vectors that are at 90 degrees to each other to create the plane. We can have a plane that is created from any two non-collinear or non-parallel vectors as shown here. Next type is a three-dimensional space, we had I hat, j hat, and k hat to describe that space, and those vectors were all at 90 degrees to each other. They don't have to be. I was able to locate a picture like this, but it still looks like it's at 90 degrees to each other, but just keep in mind that it could be a warped box or parallelepiped type of box that creates a three-dimensional space. There are other spaces of more dimensions than just three-dimensional space out there, but it gets hard to visualize that because we live in a three-dimensional world. Another thing I want to point out that in your homework you might encounter this capital R or R squared or R cubed. What do they mean? They just mean that it's a real number line, like the x-axis or the y-axis, or so it's just saying that it's one dimension. And then R squared is usually our Cartesian plane x and y, but it just basically means 2 dimensions, and then this is 3 dimensions. Let's talk about linear dependence and independence. It's going to be involving the following. We're going to be removing redundant vectors from the spanning set to create a basis for the space. So let's review. Basis definition is the smallest set of vectors from which one create all other vectors in the space. So if we are looking at one-dimensional space, the line, and you might be given 2 or 3 or 4 collinear vectors, but you don't need all of them to span this line. They will span just one line if they're all collinear, but you need only one of them to define this. So this statement right here is called a linear combination. If this linear combination is a true statement, that means A and B are dependent on each other, and we don't really need both of them to define the line. We can say just set with only vector A inside of it, or a set with only vector B inside it can fully determine this line. So this squiggly brackets right here, it's a brace. We use that for notation for a set of things. So usually we'll have more than one item inside of this set. So to summarize, a spanning set or basis set for one-dimensional space is one vector or 2 points. Moving on to the next space. We have vector A here, vector B, and this long one right here is vector D. This vector D could be created out of vector A and B, and this formula right here, which is the linear combination, kind of shows you that you could stretch A a specific amount, stretch B a specific amount, add them together and get this other vector D. So all 3 vectors span the plane, but we don't need all 3 vectors to define this plane, because vector D is created out of A and B. So the A and B are the building blocks for this plane. So we say that D is dependent on A and B. So this linear combination is true. And so we need only A and B to determine this plane. Technically, in terms of basis set, we could have vector AB as the set, but it could also be D with A, because D and A are also non-collinear to each other. So as long as you have 2 non-collinear vectors, then they will determine a plane or 2-dimensional space. So this is the summary over here. 2 non-collinear vectors or 3 non-collinear points will give a basis set for a plane. In the next picture, we have vector A here, B here, C here, and then this vector E. So we have 4 vectors provided here, and 4 of these will span this 3D space. But we do not need all 4 vectors. You could see here that E, if this linear combination is a true statement, that E is dependent upon A, B, C. So you can think of these A, B, C as the building blocks for this three-dimensional space. So as a basis, you would say either set A, B, C, or you could say A, B with E, because if you look at A, B is this front face of this box. This vector E is going to go from this corner to that corner. So it's actually poking outside of this parallelogram of the front face. So they're definitely non-coplanar. So as long as you take three vectors that are non-coplanar to each other, then it will determine a basis set for a 3D space. So here's a summary. Any three non-coplanar vectors or any four non-coplanar points will serve as a good basis for a 3D space. So in your homework, you might be given points or you might be given vectors, and the question will ask you, what do the following span? Or sometimes they might ask you, what is the basis that you need to span this space? So I'm going to do both of these parts for questions A and B. So because here we're given 3 points P, Q, and R, 3 points can form two vectors. And those could be collinear, so 3 points could follow straight in a line, but they don't have to. So they could be collinear, that's collinear, or they might be non-collinear, so they could create a plane. They cannot create a three-dimensional space because there's not enough information. So what we're going to do, because we need to check whether the vectors are all on the same line or maybe they're not, just to create the two vectors from the 3 points. I'm going to do PQ and QR. You of course could have also done PR as well, but just any two would be sufficient. So next we need to actually create a vector out of the 2 points provided. So let's do a quick recap how this is done. To create a position vector. So we have PQ pointing from P to Q, and let's say origin is a random point here. What we want to do is go from P to O and then O to Q. That creates the vector PQ. Why do we want to go through the origin? Because algebraic vectors always have the tails at the origin. So OQ vector would be exactly the same look or format as this point Q. Will have components 3, 2, 4. So point has coordinates 3, 2, 4, but vector OQ will have components 3, 2, 4. However, vector PO is not with the tail at the origin yet, so we have to change that order. So this is how we did it before. Let me show you. So you'll say PQ is PO to OQ. Then vector PO is negative OP, and this negative OP, I just changed the order here. So the components of vector OP would be this -3, -7, and 7, which are exactly the same as the coordinates of point P, -3, -7, and 7, because the vector is pointing at this point itself. And so all you have to do is this subtraction. So 3 subtract a -3 would be +6. 2 subtract -7 would be +9, and 4 subtract 7 would be -3. Then you do the same thing with QR. You could pause to take a look at the calculations here. I'm just going to move on with the rest of the explanation. So now that we have the two vectors, we want to check if they're collinear. So we had this statement from collinear or not. So we're going to see if we get a contradiction out of this or not. So create a vector PQ is equal to some sort of scale factor K and vector QR. So just take your values from before. Then take a look at the X component. So we have 6 is equal to -2 of the K's. Here we get K is -3. It actually was super obvious even from beginning that if you multiply -2 by -3, you'll get 6. -3 by -3 will get +9. And 1 by -3, you get -3. So you didn't actually have to perform this check with linear combinations. You could have just looked at it and saw that they're multiples of each other. So this -3 being the scale factor is true for all of them, even though I didn't do all the components. And what does that mean? The conclusion is the given points P, Q, R are collinear, and they span a line because they're multiples of each other, and so they span a line in three-dimensional space. So they don't span actual 3D space, but this line is in 3 dimensions because it has 3 components, X, Y, and Z. So it's a line within a 3-dimensional space. Then another part of this question is, what is the basis for this? So if you say the basis vector set, you could say any one of these vectors would have been enough to create the line. So I chose the second one, but you could have chosen the first one. And if you wanted to say the basis from points, you would say, well, we need 2 points to create this basis for this line, but it didn't have to be point P and Q. You could have said P with R or Q with R. It wouldn't have mattered in this situation because they all fall on one line anyways. Let's go on to example number B. And I noticed in my calculations I made a mistake, so I'm going to adjust the question to be 2, 2, 7 for this to work, okay? So we're given point A, B, C, D. So how do we know they are points? Because there's no vector symbols. So these are points, and you're actually told in the question these are points. So 4 points can form 3 vectors, and they can be collinear. So it could look like that, 4 points all in a straight line. Or all 4 points are going to be on one plane. So I'm drawing this parallelogram to indicate they're all going to be on the same plane. Or possibly there's going to be 2 or 3 of them on the same plane, but one of them is not on the plane. Okay, so we're going to verify which of these scenarios do we have. So as before, we're going to create vectors out of points. This time we're going to do 3 vectors out of the 4 points. I have chosen AB, then BC, then CD. You could have created any other combination. It would not matter. Your steps in the middle, of course, will be different from mine, but the conclusion about what it spans will be identical. So you can pause here to verify my work and message me to let me know if I made any other mistakes. So after you create the 3 vectors out of the 4 points, you should glance at them to see if any of those 3 are multiples of each other. So they don't have to proceed and do the algebraic calculations. So none are obvious multiples, so we could say they're non-collinear. So this situation with all 4 points on the line is out the door. It's not what we have here. So next thing we want to check, are they coplanar? So to check if they're coplanar, we do have to do a linear combination. It's not something that you could just look at and know like we can with multiples. And so here, use the values we arrived from creating vectors to create this linear combination. Then separate the components. So we have an equation for X component, another equation for the Y component, and then this third one. Choose which one to start working with. So I noticed that the 0K allows me to really easily find the scalar factor M, which becomes a half. I'm going to take this one and plug it into this equation here. Solving this gives me K is also a half. Don't just stop here though. You must check your work, because what if there's actually a contradiction in the third component we never used yet? So do left side, right side check, plug in half for the K, half for the M. The calculation here yields size 1, but the other side is size 2. So there is definitely a contradiction here. What does this mean? This means that if you have a contradiction here, that means they're non-coplanar. So points A, B, C, D are non-coplanar. And so we have this scenario here, and they span a 3-dimensional space. In terms of the basis, you could say the 3 vectors you were working with form the basis for this 3D space. Now, you might have questions where you have vectors given to you right away instead of points. So it's pretty much the same thing, but I'll just do these 3 examples. So part A and B are multiples of each other. So you could see that you can multiply A by 2 to get B, right? So check both components to ensure that that's the same. But C is obviously not. So what does this mean? That means A, B, C span a plane. So all 3 of them are on the same plane. but we don't need all three of them as the basis for that plane. So we could say the basis could be just A and C, or we could say B and C. Next. I did say one more note here before we do the next question. It can't be, the basis cannot be A and B, because A and B are multiples of each other, as you saw here, and so they will create only a line, and they will not create a plane. Okay, question B. We have vector u and vector v. Notice how vector v is actually a zero vector. It's ineffective in giving you new information. So these vectors span a line. So even though there's two of them, one of them is actually not doing anything for us. And so for a line, we only need one vector. So the basis can be only the vector u. We cannot use the zero vector as the basis here. Last question. We have vectors A, B, C provided, and you should look at it to verify that none of them are multiples. Obviously they're not. So we eliminate the fact that they're all on the same line. Then we need to check if they're coplanar using this linear combination. If we do not get any contradictions, they will be coplanar. If we get contradictions, they will be non-coplanar. Let's see what we have. So you're going to put in the vectors provided in component form, split up the x component, y component, and z component. Again, notice how this ends up having no k values, so this is the easiest one to start with. And you solve for m to be 1/3. Then you plug it into one of the equations. I chose this one. And when you solve this one, you get k's 2/3. Again, don't stop here. You have to check because maybe there is a contradiction with the other one we haven't used yet. And so when you do that here, you'll end up being negative 9/3, which is actually the same thing as -3. So there is no contradictions here. So the concluding statement would be vectors A, B, C are coplanar. And for the plane, you only need two of the vectors as the basis. So you could say A and B is the basis. You could say B and C is the basis, or A and C. It is up to you.